Okay, welcome back. So this is the last part of what I wanted to tell you, and this part will be a little conjectural because this is the kind of things that I've been thinking about over the last year or two. And so let's see what's the question we are going to tackle. We have now tried to see what all the eigenstates in string theory look like. I give you a mass m, I make it out of strings and branes, I find it just becomes a bound state whose size is bigger than the horizon, I don't get a singularity, I don't get the horizon. In principle, if I know all the bound states, I know everything because the time evolution is known, because any initial state, maybe a collapsing star, is a linear combination of all the eigenstates. And then I can superpose them in principle, evolve each of them as e to the minus I omega t, and I should be done. But of course, in practice, we don't know how to do that because I can't, superpose them, and I don't even know all the wave functions very well. But in fact, we can actually make a guess as to what the dynamical issues are by indirect means, and that's what I want to discuss with you. So my belief is that you cannot actually violate causality in string theory. I think most people would agree with that, but not everybody. And so causality just means, can you have effects outside the light cone? And I don't know actually any effect which really goes outside the light cone in any convincing way. So I will assume that to leading order, we have causality in our theory. I'll tell you in a minute what I mean by leading order. So it's even weaker than strict causality because a general manifold, maybe you can't define exact causality. But if we have leading order causality in our theory, I will now show you a picture, a conceptual picture of what should actually happen and where it should happen as a star is collapsing. Okay, so now we ask a dynamical question. As a star collapses, we've already seen that the effects are of the right order. That's what we checked by these cancellation of exponentials and all that we have these states and we have an order 1 probability for transition to those states. So everything looks sort of okay order of magnitude wise, that we won't get a black hole. But now we want to know more about exactly where the transition happens. Okay, so there are interesting effects there, and that's where the constraint of causality comes in. Okay, so here's the causality issue. Let's start with a star, and that's collapsing to make a black hole, and this is the classical picture. Once it goes inside the horizon, the light cones turn inwards, and if you have causality in your theory, then whatever I do here, even if it changes to strings, something magical, it can't actually change the horizon because that is outside the light cone. So if I can't go and change the horizon, you remember this old picture, the light cones turn inwards. So nothing here can influence the horizon, and once you have the horizon, you will keep getting pair creation, and then you have the problem. And what I mean by leading order is we had seen that even if the pair creation process is a little bit affected by order epsilon, it doesn't help, right? So even if there could be slight small effects leaking out of the light cone up to here, it doesn't help. Okay, so once you actually get in here, you have a problem. So in fact, what we really need is somehow this collapse should stop before it actually goes through the horizon. Otherwise, all these things which we estimated, they would really need to have effect going outside the light cone, and that we haven't seen in string theory. Okay. So as we said here, if causality holds to leading order, then this region will create the pairs, and then because we had this inequality, even if you make small corrections, the entanglement just keeps growing and growing, and then we have seen that everything is completely gone. Okay. We can't save it. So what exactly is the place where we need to save everything? Let's be very careful about that. Suppose we start with the object of mass m. It could be a black hole, and now we know it's like a fuzzball, so let's take that. And suppose I throw in a shell of mass m prime. That's a shell. I haven't drawn the whole thing, but that's my shell. And the shell is coming closer and closer. Where should something new, which is not in classical physics or semi-classical physics, start happening? So now we are working backwards in terms of requirements. I'm not actually going to show you that this is what happens using string theory because I can't calculate such dynamical things. Now I'm just trying to say, if causality has to hold, where must something happen and what must happen? Let's just try to force that kind of an argument through. So now the new horizon will be at 2 times m plus m prime. That's okay. Now we will set g to 1. It's 2g m plus m prime. Let's even set g to 1 to keep the slides clean. Okay. So if nothing happens at this location, this dotted location, 2m plus m prime, suppose the shell comes in here, still not on the surface of the fuzzball, suppose the shell can come in here. I'm already in trouble because now the light cones here will turn around, will tip, and now whatever the shell is doing and the stuff inside is doing, it can never influence the outside, and you can see I'm in trouble. Okay, so it's very interesting. The place where something new must happen is not when the shell reaches the fuzzball. You can say the fuzzball is a place with a lot of strings and so on. If it reaches there, maybe new things happen. No, I need the new things to happen here, this dotted line. And where is this dotted line? It's at a position which depends on m prime. If I'm throwing in a test mass with m prime almost 0, then it can come all the way to the surface here and then see new things. But suppose m prime is 0.1 times m. Then the effects have to happen at 10% of the horizon radius outside. It's a 3 kilometer black hole. This has to happen 300 meters outside. If I put m as 0.2 m, then it has to happen 600 meters outside. Okay? And if I throw a point mass like this, not a shell, you can also compute how much the horizon bends. I mean, the same kind of calculation where the horizon is. That's the distance from the horizon, where from the old horizon, where the new horizon forms, and so you can see how it grows there. Okay, so what are we looking at now? We said we now look for requirement from causality, and the requirement is this. Somehow we have to get a picture of how space-time behaves, where if the shell is coming in, if it is low energy, it sees nothing special here. It can come all the way here. Low energy matter sees nothing special, but matter with high energy, suppose this mass was 0.1 m, it should see new physics. It should start becoming a fuzzball. So it's not like, so people always ask the question, how far from the black hole do your new effects start? And we are not now seeing that's not the correct question. The question you really want is, that question depends on what's your mass. If you're a very light object, you should be able to come all the way to the surface of the fuzzball at 2m. And if you're a heavy object, you should see new physics here. If you're even heavier object, you should see a new physics there. Okay, do we know any model in physics where that happens? Let's go searching for models so that we can build some intuition using them. And actually we do have such a model, and the model was actually comes from a simple, completely solved string theory. The string theory in 1 + 1 dimensions actually was completely solved in the late 80s. Okay, and early 90s. You don't actually need to know anything about it. The only thing we'll take from there is the final picture which was obtained, and the picture was like this. So this is what a picture of a Fermi fluid. So it's a Fermi sea. So you know, if you have fermions in a metal, you fill the lower energy levels first, then the higher levels, and then the higher levels. That's the Fermi sea. Okay? If you have a Fermi sea and everything is just filled up to the Fermi level, what's the dynamics of the Fermi sea? Well, you can make a distortion on the sea. You can shake the electrons in one place, and then the waves travel on the sea like this. In fact, the traveling of these waves can be mapped to the motion of a bosonic field. It behaves like box phi equal to 0. So one way you can, in 1 + 1 dimensions, fermions and bosons basically can be interchanged with each other, and this is the reason. The fermions fill up a Fermi sea, you make a distortion of the sea, it actually acts like a bosonic wave, which is just going like this. Okay, so what we are going to do is, what happened in the C equal to 1 model though, was the depth of the Fermi sea was not actually uniform. It was like this. Okay, now that's very interesting, because look at this picture now. Suppose this was my bosonic field. If you just thought of it like a boson, okay, it's just on the surface of the sea and you don't care, the sea could be infinitely deep, it doesn't really care, it just keeps moving, box phi equal to 0. But now we realize that can't be the right physics, because what you see here is that if this wave is like this, suppose the wave at here doesn't notice the bottom of the sea. But if the wave was very tall, then by the time it comes here, it will start hitting the bottom, and then the wave dynamics will distort. If it is a very small wave, it can happily keep moving, by the time it comes here, then it will distort. And so now you see, this is the kind of picture we need. A heavy wave will actually start seeing the physics of reaching this is the surface of the fuzzball, let's say. A heavy wave coming in will see physics here, a lighter wave will see it here, even lighter wave will see it here. So we really have to interpret our particles, our scalar particles, as really something which are waves on the top of a sea, and the sea is actually getting shallower as we come up to the fuzzball, and you can think of the fuzzball as the actual land. Okay, that's what we need. So we've got to see if we can somehow come close to this picture, but let's just be clear about what we have learned now. It means that space-time shouldn't just be thought of as a manifold. If you do that, you can actually never get out of the black hole puzzle. It's really, you should think of it as a manifold with a thickness, and this is a picture of the thickness. And then the wave that you're actually that's coming in, it responds to the thickness. As you're getting thinner and thinner, as you come to the surface of the fuzzball, it's not like outside there was ordinary space. It may look like it, but there's an extra parameter to space-time, like the thickness, and when you hit the bottom of that thickness, new physics happens. And you can see this is what we wanted, right? More energy reacts farther out, low energy reacts further in. Okay, this is just a picture. Is there anything we see from which we can get this picture? So we'll actually, so where does this picture come? What should happen outside the fuzzball to change the physics here to a varying depth C so that different guys see something? I shouldn't just have white space here, otherwise it looks like nothing is happening there. Where can new effects come from? Well, if I look at the virtual fluctuations in this region of all the fields in my gravity theory, well, that depends on what is sitting here. If I had empty space here, as opposed to an object here, you can imagine the virtual fluctuations here, even normal QFT, can be different, because this object can emit a particle, a virtual particle, and can emit more virtual particles. So the virtual fluctuations here can change depending on whether there was something here or not here. Okay, and what I'm going to argue is that virtual fluctuations, in fact, let's think about them more carefully, and they are actually going to give me a property of the vacuum in quantum gravity, which would actually give me this kind of varying depth picture, and only then we can get away from the causality problem, and it will also tell us how exactly the semi-classical approximation should break down. Okay, this is just a picture still, and let's see what questions we have to answer. What is the nature of the fluctuations we are interested in? Well, quantum fluctuations are small things. Why should they be important? Okay. And thirdly, can we pinpoint the effect they should have on something trying to fall in? Okay. So the fluctuations we are after are rather simple. If you have a fuzzball of mass m, you can always have a virtual fluctuation to a fuzzball of larger mass. Just like this room could be empty, and you could create a particle-antiparticle pair, electron-positron pair. Now that has a larger energy. It's only a virtual fluctuation, it will die soon, but you can fluctuate to larger objects. And so I'm actually looking at these fluctuations. Okay, so at least I've pinpointed what kind of fluctuations I'm conjecturing would be relevant. Second, why should they be important? If you have a big fuzzball and you fluctuate to an even bigger fuzzball, well, that's a huge change in mass, and so these should be exponentially suppressed. You can always have a fluctuation, but if it borrows a lot of energy from the vacuum, it should be exponentially suppressed. Why should I care about such fluctuation then? And that's because the number of these fluctuations is very large. If you take fluctuations whose total mass is m plus delta m, the Becquerel entropy of that, expression of that is the number of these possible states. We already argued in checking orders of magnitude over there that this exponential is very important, and we are going to now conjecture it can cancel the suppression of these fluctuations. So they are going to be important to me. Okay, good. So all these tools we've developed so far, we're just putting it in together to see if we can get a possible picture. And so what we have learned so far is that not only is the inside of the black hole different, it's filled by a fuzzball, even the outside, we should think of this as a place where the virtual fluctuations are sort of pretty important here, maybe a little less important here, and so on. And so I just call this, normally people call this area Rindlow space in some coordinates. Let's just call it zero Rindlow space because the quantum fluctuations in this region are different from the fluctuations of ordinary space. Okay, now let's see if we can actually build a picture. You can already now start seeing where the picture will come from. So out here you have virtual fluctuations of fuzzballs. So suppose this is mass m. Virtual fluctuations take you to 1.1 m are up to here. Fluctuations with mass 1.2 m go up to here, and so on. They are bigger fuzzballs. Suppose a shell is coming in with a mass of 0.1 m. So when it is out here, it's just a fuzzball. There are virtual fluctuations of mass 10 m here, but it can't actually excite them because it doesn't have that much mass. But suppose that fuzzball comes all the way up to here. That's shell, not the fuzzball. The shell comes up to here. Now the total mass available to the system is m plus 0.1 m. Now the virtual fuzzballs which had a mass 1.1 m are now actually all accessible. So in fact the shell at this location, at least energetically, is in a position to transition to those virtual fuzzballs. Now if you start with a bigger shell whose mass was 0.2 m, then when it comes up to here, it has enough energy to transition into the virtual fuzzballs, therefore extending up to here. And if the shell was very light, like 0.001 m, it just can't do anything with those virtual fluctuations, come all the way to here, and can't convert them to actual on-shell states. So again, we are slowly trying to build up the picture. These are all still pictures, but trying to put in a picture of what might happen if we have virtual fluctuations. So we have seen the fuzzballs, so there can be virtual fluctuation fuzzball. We've seen the degeneracy, we know, the Becquerel entropy. So we're trying to make a picture using that. Well, now we actually have to see. This is the last part of the thing which is completely conjectural. I now want to show what I've said in pictures. As a shell comes into that place, I've said at least has the right energy to turn into a fuzzball at that radius. What process exactly makes it turn into a fuzzball and not just continue in? If it continued in, it would be causally trapped and I'm finished, right? Then I can't do anything. I'm actually looking for something which will actually make it do something at that location. It's something I call the Vector hypothesis for reasons which I'll tell you. Nobody likes this acronym, so if you don't like it, that's fine. Okay, but I couldn't think of anything better, so for the moment, that's what it is. So let's return to the main problem we have. We want to see the actual mechanism by which this guy might go here. Okay. So here is the way we are going to argue. Since fuzzballs exist as objects in the theory, we also have virtual fluctuations of fuzzballs in the vacuum. Now I don't even have a black hole or anything. Even in this room, there have to be virtual excitations of these fuzzballs. So what kind of objects are these? You of course have virtual fluctuations of electrons and positrons. Can you also make maybe a positronium? Can you have virtual fluctuation makes a positronium? Sure, in principle, why can't you produce that? It's a possible state. Could you make like a whole atom? In principle, yes. Could you make something like a benzene ring? Yeah, anything which can exist as a real object can also be a virtual fluctuation. Why don't we worry about benzene rings hanging around in this room as virtual fluctuations? They can, but they're very heavy, so it's highly suppressed. But that's the kind of guy I'm now looking at, because if you look at these fuzzballs, if you look at these examples we had made, this is sort of a cartoon picture, the Euclidean short shell geometry I had shown you, just a cartoon of the kind of metrics we actually have. So I get some kind of an extended object like this, and that's one of these virtual objects which I am looking for. And again, it's very heavy, and so you might think it's highly suppressed. That's why we don't worry about benzene rings in the vacuum here. But again, what I'm going to use is the fact that degeneracy is very high, and so in fact I'm going to argue that any one fuzzball is a rare fluctuation, but a set of all fuzzballs is an important component of the vacuum. So I'm just going to make it sound reasonable. I can't, of course, prove it. Okay? So I'm going to say that this is an important component of the vacuum, and I'm now going to argue what this vacuum can do for you. The third property of these things I need is, if you go back and look at the fuzzball, these structures I gave you, they're actually very resistant to compression. So if you take a look at the Euclidean short shell geometry I gave you, if you try to squeeze it, it just fights back. Okay. So why do things not like to compress? If you just take a string, that's also a big object, but a string is happy to compress, actually wants to squeeze. But these guys actually don't want to compress, and in the end that's for a very, you can see it of course by looking at the structure, but it's also for a very deep conceptual reason. We know that it's generally believed that inside an area A with mass m, you can't put more than the Becquerel entropy worth of states. That's the optimal packing of states. We normally believe that. Okay, so if it was easy to compress these fuzzballs, you have these many fuzzballs which represent all these states, suppose I could easily squeeze them, maybe very little cost energy, to half the size. Then all the states have gone here, and so I've held that much entropy in half of that region, which 1/4 of that area. As long as we believe that you can't, that this is the optimal packing, the Becquerel entropy, I should not be able to squeeze them. Okay. Anyway, if you play with that game in a little bit of detail, you can even figure out what's the equation of state for these guys. It's a very stiff equation of state, actually the stiffest possible. It's P equals rho, which means you can't have more stiff than that, because otherwise the speed of sound becomes more than the speed of light. Okay, so this is the property of these fuzzballs, and so I've just assumed that that's the property these virtual objects share. So now let's just summarize what I have said so far. The vacuum has an important component consisting of these virtual objects. They are extended in size, like this extend means they're not point-like, they are these big objects. They are compression-resistant objects, and that just, for short, I'll just call it vectors. Okay. So it's a funny thing, I'm just saying that around each point in this room, I have all these virtual objects which are there in the vacuum, and I can't stop having them because they exist as real structures. Then in the gravity vacuum, they'll also exist as virtual structures, and they are important again because they are a to the s of them. Well, if they are there, what do they do? For normal things like a star, they don't do much. This is a vector. I won't draw the hole inside. Suppose this is the vector. It doesn't want to compress. It's a virtual fluctuation around the origin here. Suppose I put a star in here. The star has a gravitational attraction, and this guy squeezes a little bit, but doesn't really want to squeeze, right? It's very stiff. So it's okay. Squeeze by a millimeter and just stays put. So nothing much happens. Okay. When will something really interesting happen? Let's go back to what happens when we make a black hole. You remember this picture? You have a star. The light cones turn slightly inwards. If I make the star smaller than its own horizon, then the light cones have completely turned inwards, and you can't even stand at one place. You have to keep compressing, right? Keep compressing and you go to zero. That's the classical picture. Okay. So that was the old problem with the black hole. And now let's see what happens. Take this region and suppose just have a horizon with just empty space inside, like you have in the standard picture of a black hole. And just imagine one of these virtual fluctuations. The virtual guys follow the same rules of dynamics as real guys. Because the light cones point inwards, they have to keep squeezing. Well, that's funny. The vectors could not be squeezed. Or rather, they could be squeezed only at a great cost in energy. We know their structure. Okay, so if I can ever get into a situation where I actually have a horizon, this vacuum is in some trouble. Because these guys are now going to continue to squeeze. And they don't want to do that. Or rather, if they want to do that, the energy for that has to come from somewhere. Well, where can it come from? So if you look at the star again, here the star, and this is one of the virtual fluctuations which I've just drawn superposed on it, and the light cones are going in. As the star tries to go into its horizon, if it actually went to the horizon, it will actually get into trouble. This is what will happen. And so the argument will now be that the star doesn't want to go into the horizon because this virtual part of the vacuum is important, and it doesn't want to compress. So in fact, as this guy comes very close to the horizon, there's an enormous stress on these guys, because now the force required to stand at one place and not get compressed when the light cones are almost tilted is enormously high. That enormous compression on this virtual guys changes their wave functional and therefore distorts the virtual fluctuations into real ones. So it's a little bit like the Schwinger effect. Imagine two parallel plates which are kept here, and then the virtual electron-positron pairs are there. right? But as we talked about before when we were talking about this the other day, if the plates are not far enough, the pairs can't actually become real. They need to go far before they can actually become on-shell particles. Let's let the separation be a little less than that. Okay? So you have lots of virtual pairs like this, but let's imagine there are lots and lots of flavors of charged particles, electrons, muons, and so on. There are lots of flavors. So now the vacuum is full of a lot of these virtual guys, but they're not real guys because I haven't allowed this thing to become big. Okay, so this vacuum has a lot of vacuum fluctuations, and now I'm going to slightly move this plates apart. At some critical distance where they can actually become real, if I had, let's say, 1 billion flavors of these particles, the vacuum suddenly crashes and produces lots of on-shell particles. Okay? So you may think that if you first did a classical approximation and said, I don't care about virtual fluctuations, you don't know all the virtual guys are there in the vacuum, and then as you suddenly cross this typical distance, you will say, the critical distance, you will say, hey, where did all these particles come from? But in real fact, if you take the quantum physics first and don't ignore those virtual fluctuations, as you cross that limit, you suddenly get an enormous effect. So it's a little bit like that because there's a large number of these guys here. As this guy tries to crush them past the region where they are not happy to exist, the stresses on these guys are enormous. The vacuum wave functional changes. The energy to change the wave function has to come from this guy. So the energy of the star gets drawn out and gets converted to the energy of these guys. But these virtual fuzzballs, of course, now when they turn to real fuzzballs, you have the fuzzballs you wanted. So in fact, the picture that I seem to be getting forced into is that I have these eigenstates on the one hand, which look like these virtual fuzzballs, but the way that causality forces us to a dynamics of these fuzzballs is that it says that somehow a vacuum which has these virtual fuzzballs, which must exist because something is a real object must exist as a virtual object, in this situation you can't make closed trap surfaces. A closed trap surface is something where the light cones turn inwards. Once you make a closed trap surface, you have to make a singularity. The horizon then can't be blotted out. It will always be there. You'll always have the information paradox. But this vacuum now wants to fight ever making a closed trap surface because these guys don't want to compress. And I think that is my dynamical picture for what actually happens when the star is actually trying to pass through its horizon. Okay? It looks very non-local, but it's not. I'm not actually violating any causality. If you have a vacuum which is already sitting there for a while, then in fact it can develop correlations over long distances. That's not a violation of causality. It doesn't mean you can send a signal from somewhere to somewhere faster than the speed of light. It's just like if I put my two parallel plates there for the Schwinger effect, the vacuum polarizes to create electrons and positons in that vacuum, but the theory is still completely causal. You can't actually violate any causality there. And I think that component of the vacuum, to understand these extended objects exist, I think is essential, because without that, I don't have any picture where I can actually make the star not go in, and once it goes in, even though all these estimates for tunneling and all were okay, they will still have to violate causality. And if I ultimately find I can't violate causality in string theory, then I think I'm left only with this picture. But this picture is true. I can't actually prove it any further to you. If this is true, it actually leads to some interesting situations, because if the vacuum really has these extended fluctuations everywhere, which are important because of the large entropy, then actually this has an interesting consequence for cosmology. And so let me take a little bit of time to talk about that. This is a complete conjecture, of course, but let's just have some fun. Yes?
Before you go to cosmology, while we're still thinking about this, if I throw ordinary matter, shell of ordinary matter to it,
Yes.
is the transition to the fuzzballs instantaneous as you go through the horizon, or does it take some time?
It takes some time, because all that is happening is that as the shell is coming closer to 2m, the virtual objects are getting compressed more and more. So it's about as instantaneous as if you took the Schwinger plates and then you move them past their critical distance where the on-shell particles, the off-shell particles become on-shell, and if there were many flavors, they'll just all crash on you. But they won't crash on you instantly. That takes a bit of time, and it's that kind of effect. The vacuum is already heavily polarized by these guys being there, and as this shell tries to come in, so somewhere around, let's say, 10 Planck lengths, you start converting some virtual things into real things, and then, by the time you come to 1 Planck length, it's probably all gone. That would be my mental picture. Yeah, okay. Yes?
Some similar question. So this object that you're talking about has some kind of resistance.
Yes, the virtual objects have a resistance
Yes,
to it.
but you're suggesting that this resistance is something like delta function, but it should be continuous.
It is continuous. So when I said compression resistant, I didn't actually say incompressible, because nothing in a theory which has causality can be really incompressible, right? Everything is only compression resistant. And that's what I tried to say here, that in fact, if you take into account how stiff they are, you can compress them. They do have just a pressure, and they have a stiff equation of state, but they can be compressed at the cost of energy. So if you, as an infalling shell tries to compress them, the energy has to be drawn from somewhere. And so the picture is that the shell is collapsing. Some part of its energy goes into these virtual guys. So the remaining shell has less energy. Okay? And so now the horizon sort of moves further in, right? With less energy, the horizon will be smaller. It tries to come close to that horizon, but as it comes close to that horizon, more energy bleeds into these fuzzballs, making real fuzzballs, and the shell has even less energy. So somehow it keeps chasing its tail and never actually crosses its own horizon, because that's the place it can't cross. So in the end, you just get a fuzzball.
Okay, but in the process of collapsing, the star should sense some kind of resistance.
And so in this case, I'm arguing that it will, in fact. This is a resistance.
But I mean, no. Before it reaches the point that we usually call event horizon.
Yeah, so I don't know how much the distance is where it starts feeling it. My conjecture would be its order Planck length. That's why I just said at 10 Planck length start feeling it significantly, but there's a little bit of resistance at all distances. That is true. Absolutely. There's a little bit at all distances. I'm just thinking it becomes very sharp as you start approaching 2m, because inside that you really can't go.
So the function would be something like this.
Yeah, I think it's fairly sharp. Again, I can't prove that it is sharp, but my prejudice would be that it is fairly sharp. These are all just prejudices. So I think the part which I think you can't get away with, the details of this, obviously there are none, right? I'm not giving you any details. But the argument here I think is important, that if you believe in causality, you have to stop the guy outside. You already know the eigenstates in string theory. Let's accept all guys are, for all cases, you always get a fuzzball and not a black hole. If you accept the way the fuzzballs work, you know the eigenstates, you know that putting them together has to give you the evolution, and you know you can't violate causality. If you put those things together, I think you can't get away from this picture. So if somebody can find another way around, of course I'm not trying to prove anything to you here, but if you can find some other way around, I'd be happy to argue this point. Okay. But let's assume this for the moment, and just let's try to have some fun with cosmology. Okay, so let's make a toy model for all these vectors that we were dealing with. So as we said, they are compression resistant. I'll just take a toy model, and the toy model says if you compress them, by a little bit nothing happens, but let's put some maximal compression. If you compress them to smaller than, let's say 0.9 times their size, let's say they just can't compress at all. So I'll put no penalty for compressing by a factor, less than alpha, but if I compress them by more than alpha, they don't want to compress. Okay, so this is just like a step function. Of course, it's not a step function. I'm just taking something simple for illustration. Okay, so let's start with flat space. I'm just going to make a 2D Euclidean space just for rough arguments. And then around every point, you have these virtual fluctuations, which are extended objects like this. And they don't want to compress. You can't compress by more than 0.9. Okay. Suppose someone takes this and tries to take this sheet of paper and tries to bend it into a bowl like this. Okay. So what happens? These very small circles, their fractional compression is not much. Okay, if your curvature radius is this big and this is only 1/10 of that, it's compressed by a factor of 0.95, and that doesn't mean much. Okay, so that doesn't worry me. But if I compress this guy, if you look at this circle here, it's been compressed by a factor like 0.7 over here, and that's not allowed. Okay, so that's interesting. If I take this sheet of paper and I try to give it a uniform curvature, doesn't matter how much the curvature radius is, if I keep going and going for a long distance, at some point I run into trouble because I'm compressing some vectors by order 1 and they don't want to compress. Okay, so let's see what that means. How do I mathematically put that down in some symbols? So again, this is the same thing copied from the previous slide, that I'm not allowing compression more than some amount, and now we see I can't do this because then this guy is compressed by more than the 0.9 that I allowed myself. The mathematical condition this gives you is sort of interesting. You can't write it as a change of the effective Lagrangian. It's not like you can write as some other higher r square, r cube terms, which is what you normally do for effective theory. It's a more global kind of condition. In fact, what the condition tells you is that you can have any curvature radius rc, let that be the curvature radius of this region. There's no constraint on rc, but you can't maintain that curvature over lengths which are more than rc. So I can have, suppose I take the curvature radius to be 1 meter. I can have so curvature radius is like a 1 meter curvature radius bowl. I can do this curvature radius for, let's say, 10 centimeters, and then I can flatten out. That's fine. No vector will get compressed very much, and there's no problem. You won't even notice it. But if I maintain the same curvature, and I keep maintaining it for about a meter, I get here. And now the vectors are compressed by order 1, and I can't have that. So the condition is that the curvature radius rc can only be maintained for lengths less than rc. Okay, so it can't be really squeezed in like this, not this kind of a condition. And then let's see what this does. So if you take a star, the radius of the star might be, just for illustration, let's say it's 1 mile. But the curvature radius is quite low, quite large. It's 10 miles. So I have a 10-mile curvature radius, but after 1 mile, it basically stops. Okay, so a star sees nothing. There's no real change for a star, no significant change for a star. When do I actually have a situation where the curvature radius is 1 mile, and I also maintain the curvature for a distance of order 1 mile? When do we get into that situation? Only in 2 cases. 1, when you get near the horizon of a black hole, and 2, when you get to the cosmological horizon. In both cases, the same curvature is maintained and maintained and maintained for a distance, when the distance where the curvature is maintained gets to be of order RC. So somehow this is automatically forcing you to a situation which you can't actually absorb as a renormalization of the normal effective action. It's more like a sort of condition which looks like this, and it doesn't seem to do much for a star, but does seem to, in the black hole you've already seen that, it doesn't let you go into the horizon, like it sort of blocks you from going in, and so on. And these virtual guys in the vacuum, because they're these extended guys, they are sort of changing your physics. Okay, so let's just have a little bit more fun with this. We actually do want to get a universe which has a curvature that goes on and on, right? We do want to do that, and so how can we do that? Well, you can do that, and the reason you can do that is that, okay, I'll come to that in a minute. The vectors also actually, let me see if I just have a slide there. Yeah, so if we have said it for a black hole, if this is my virtual guy, it actually can't exist inside the horizon because I have to keep getting compressed. If I just do a time reversal on that, it also tells me something about cosmology, because cosmology is the time reverse of a black hole. So in fact, the light cones actually make what are called anti-trapped surfaces. If you take a big enough piece out of a dust cosmology, the light cones point purely outwards. So just like here, a vector had to keep getting compressed, a vector which is out here has to keep getting pulled apart. So actually vectors can't exist here because they'll just be torn apart. Okay, we know their structure, they'll just get pulled and they'll break apart. So vectors actually, in an expanding cosmology, they can only go up to the horizon. Okay, so we are just realizing that there are some interesting properties to learn about the vacuum which might be relevant to cosmology, because once you have forced this picture from black holes, well, the same picture should actually come and apply to cosmology. So now, if all this is true, we seem to be finding there's a whole component of the vacuum that we should worry about in quantum gravity, which is the vector distribution function. So for the vacuum, it was just like you could, for the normal flat space vacuum, the vectors are of all sizes around all points. But in cosmology, you can have them up to some size, but not beyond the horizon. So the number density of vectors has to drop, and somehow this is an important part of describing the vacuum. It actually turns out that if you don't think of vectors at all, you can get yourself into a sharp paradox with cosmology. You can make a paradox which is just like the black hole information paradox, but you can make it for cosmology. So give me 1 second to just draw it here for you, because I don't have it on my slide. But the paradox is exactly as sharp as the paradox that you have for black holes. And then you can see from there that these vectors, if they are not part of your gravitational theory, you actually have a problem that you can't get out of. And the problem is like this. If you take a dust cosmology, which is, let's say, I'll just do t to minus t, so it's contracting now, but that's just a time reverse. And in that, if I take a ball big enough, a dust ball big enough, then it looks just like the collapse of a black hole. Okay, at some point it'll go through its horizon. If I take a dust ball, at some point it goes through horizon. Maybe people who have played with this would know this, that the evolution of a dust ball collapse into a black hole is exactly the same as the region which you mark out. Here, of course, there's dust everywhere. If you mark out a region like this, the interior dynamics of this is exactly the dynamics of a black hole collapse. But if you now assume that the Birkhoff theorem is true to leading order, the Birkhoff theorem actually tells you that what happens outside a spherical ball is actually irrelevant. Okay? If I assume the Birkhoff theorem is true, then the whole dust outside, which was everywhere in a slice of dust cosmology, it can be replaced with the vacuum. So now I just have this. So the evolution of this ball should then just, I replace the outside with a vacuum, and now I'm back to black hole collapse. So the dust cosmology plus Birkhoff theorem brings it back to the black hole problem. And now I have something funny. In cosmology, we know that nothing has actually happened at the horizon, because we can see many patches of the horizon up there in the sky from earlier times. Nothing happens over there. So if I'm not going to change this to fuzzballs in cosmology, there has to be a difference between the black holes and the cosmology case, and the difference we have just seen, the actual vector distribution is going to be different in the two cases. So we can argue about that in more detail maybe later. I just wanted to mention that because I do the vector distribution function. And so now you can see what you would actually do to get, let's say, actual uniform curvature like a cosmological constant. Same model as before. We don't want to compress by more than a factor alpha. Now I want the curvature to actually keep going. The curvature radius is RC, but I want to actually keep curving to a distance L more than RC. I can keep doing that as long as the maximum size of the vectors in my space, I can have small vectors, bigger, but no vector is bigger than this. If the maximum size of the vector is connected like this to the radius of curvature, then in fact there is no problem. I can keep maintaining the curvature all over. No vector is actually squeezed by more than the factor alpha which I had allowed myself. So in fact, this component of the vacuum actually tells you that there's going to be, you somehow get forced to the requirement that the distribution function of these extended objects in the vacuum are different between flat space and an expanding cosmology. And if I don't assume that, I can get into the same troubles I got with the information paradox also for cosmology. Well, so here's a summary of this picture, and I'll close in a few minutes because I know it's getting late for everybody. So you have these virtual objects in the vacuum. You can't help getting them because the actual eigenstates of the black hole look like that. Why did they have to be there? We knew the Becquerel entropy, so the e to the exponential of those guys had to be there. They don't actually have horizons that solve the information problem, but that means they have e to the s states of an extended size in our theory. So up to there, we are almost forced by the black hole puzzle. Once we have them, they are part of my vacuum because any real guy also comes as a vacuum fluctuation, and there are so many of them. And once I have these, well, they're giving me a picture of how the black hole puzzle is solved while keeping causality intact, because otherwise I had a great trouble with causality. I didn't want the guy to first go in and then try to tunnel out because I don't think it can. And then if you assume this, then you can start wondering what it means for cosmology, and there I was just playing around. I mean, I seem to be getting to that picture, but I'm sure there are many things open which I don't know. Okay, so let me make a complete summary of everything and then stop. So the final picture we have come to for black holes is that the interior of the black hole is not like the usual thing, but also the exterior is not, because the vacuum fluctuations here are very important, and they give rise to a picture of an effective varying depth C, and so you should really think of waves moving on space-time not like a manifold and you move on the manifold, but the manifold has a thickness, and as you come to the surface of the black hole, the thicknesses get smaller and smaller and then actually become zero, and that's the interior of the fuzzball. So this is like sea and this is like land, but the sea also has a varying depth and you are coming close to the shore here, and so larger mass objects sort of turn into fuzzballs here or here or here, wherever they have enough energy, so the total energy of this plus this can realize the virtual fuzzballs and make them on shell. So I think that's the only picture you can put together if you want to maintain causality and put it together with solving the information puzzle. Okay. So let me just conclude by just putting up a slide as to what are the alternatives to the fuzzball puzzle. So to me it looks like a logical solution because every time we have tried to make a bound state of things in string theory, we keep getting that. Okay. But all the other approaches to the problem, they go in the following way. So if you actually don't want to have a horizon, it's very difficult because you have all these no-hair theorems, and you have to go to the whole string theory and do all these complicated things, and then we have found indeed the no-hair theory is violated, you get a complete set of hair, and those are the fuzzball states. Now if you don't do that, you can go exactly the opposite way and say, no, I have my old picture of the horizon, it's a vacuum there. Okay, so now you really have the information paradox back because you will get the pair production and so on. So then what can you do? So all those other solutions that people have proposed, as far as I just try to list some of them here, but they all require some kind of action which is outside the light cone. They require a causal propagation. And so for example, you can have non-locality on the scale of the horizon radius, like you can just have non-local physics. And again, I'm not very much in favor of that because in string theory, I've seen everything being exactly inside the light cone, so I don't know how to go order M outside the light cone. Maltz and Susskind had an interesting picture where they had non-locality in even bigger scales. So this is the black hole, this is the Hawking evaporation, this is from their paper, this picture. These are the particles that have radiated out from the black hole, and they tried to argue that every particle which has been radiated is secretly connected back to the black hole through a wormhole. Okay, and so you have non-local effects across this distance, and so the particles which are emitted out very far from the black hole they reach, if you catch them, those degrees of freedom are actually connected, are the same as degrees of freedom inside the black hole. Okay. So then you can have some kind of non-local identifications, and they try to make some theory like this to, it's not clear to me how it gets you out of the black hole puzzle, but this is the picture they proposed, but it's a very massive kind of non-locality because it goes across very long distances, and people have tried to make this more precise, but I don't see any evidence of this in string theory, and I actually wrote a paper showing it gets into some trouble, if anybody's interested. There's some recent work of Hawking, Perry, and Strominger which tried to say there are degrees of freedom sitting at infinity, pure gauge degrees of freedom sitting at infinity, and somehow they are relevant to solving the black hole puzzle. I don't see how the degrees of freedom can do what one might hope, so that has actually not been clear, I think, to anybody. This thing is interesting, but it really requires black holes to behave differently from normal objects. We have not seen evidence for that in string theory, because as we said, we have a continuous coupling, the string coupling, and if you make the coupling 0, you just have ordinary strings and branes, and you can compute the radiation from it. And that rate already matches the Hawking rate perfectly. So as you increase the coupling, it just keeps matching. And you can actually follow the states for these simple 2 charge holes from 0 coupling all the way to the strong coupling when you have a black hole. And we have seen the string just swell up and up. The metric was known to us all the way through. And we don't see any change or any new kind of physics coming in. So I don't actually see the evidence for non-local physics. And if you're not going to put any non-local physics, you have no choice but to blot out the horizon. And fortunately, string theory seems to do it automatically and gives us structures which never make a horizon. And I think that would seem to be a self-consistent solution to the whole puzzle. Okay, I'll stop here. Thank you. Yes?
Is there a probability that a neutron star will tunnel to a fuzzy? Why not a probability?
It's certainly non-zero, right? But the reason it is small is the following, because your neutron star, let's say, is this big, and for the same mass, the fuzzball, let's say, is this big, because that's the black hole size, right? So let's again do the entropy matching calculations. So again, I will get the final number of states is S Bekenstein of M, so I have this positive exponential here, right? But then I also have e to the minus S classical, that's the negative exponential, and they were just cancelling. But when we computed this, a length scale had to be put in, right? There was a length scale R of the order of GM which I put in there. Now the length scale I put in is 10 times bigger for the neutron star. And now you see this is highly suppressed, because S classical had 1 power of 1 by G from the action, then 1 power of whatever radius you are putting square, and then radius to the power 4. This is from d4x, this is from the curvature's length square, so it looks like radius square over G. This is the radius of the starting star. Because the process goes over that kind of a length scale. If I put this equal to Gm, then I get the same as this answer, and the exponentials cancel. If this is 10 times Gm, then this guy is 100 times more because it's squared. So I get e to the S Beck, and then I have e to the minus 100 times S Beck. So because you have two exponentials fighting each other, if I give this an extra factor, they are not going to cancel. And so it's completely suppressed. I mean, the e to the S Beck is helping you, but it can't really help you because this guy got an extra factor. So in fact, you could think of the black hole sort of backwards. The horizon is the place where the guy keeps squeezing and squeezing till the point where the probability of accessing the rest of phase space becomes compared to the action for tunneling. And you can call that the size of the object. In fact, if you go back to the actual fuzzballs, the ones made with strings, all explicit solutions in string theory, you can see why you got that particular size. You can look at the solutions and see it. And the reason is in some sense very simple. Because in quantum mechanics, you can only hold one state per cell of phase space. We talked about it. It's just like you can't hold too many states at one place because orthogonal wave functions should have no overlap. So you get one state for every delta x delta p of the order of h bar. So here you have a vibrating string which has e to the s states. If you narrow the string down to a very thin region and say, look, I don't want the string to go outside this tiny ball. This is a short radius, but say I look at only states we don't go outside this ball. Then there are very few states. Okay, but turns out if you look at only the states which stay in a string that tight, it actually has an entropy equal to this much area. It just keeps tracking it all the way through. And so the reason the string vibrates up to a size whose area then gives the Bekenstein thing, the reason it occupies all that size, which grows with the number of states, is that many orthogonal states can't fit at a point. It's basically just phase space. If you want to hold a large number e to the s of states in a region, you've got to have a biggish region. And that's how you can just roughly see why it's swelling up. So in some sense, anytime you really had a complete theory of gravity, you're going to make all the states, the guy had to swell up. I mean, they wouldn't have gone to a point. So once you have the states, they've got to be like this somewhere. Yes?
In the previous slide, you give a thickness to the manifold.
Yes.
Does that mean adding an extra dimension, space dimension to the metric?
Okay, so it's not a space dimension. This is just a schematic way of showing that this manifold has an extra property that we need to think about. You can model that by an extra dimension, which is, I'm calling that the depth. So so in a way you're right. I'm saying that when we see a scalar field, we think of it as motion on just a maybe manifold, 3D manifold, but that's the wrong way to think about it. Think about it as a wave on the sea, but the sea also has a depth, right? But I don't think of that as a physical dimension. The depth basically means think of all the virtual fluctuations which might be existing there of all these virtual objects. If there are more virtual fluctuations in some place, let's say that that place has a shorter depth. Okay?
It doesn't have any effect on the integral measure.
On the what measure?
The measure in the integral, dx.
The measure in the path integral?
Integral.
Or the normal integration, d4x, the integral d4x.
Yes.
Yeah, so what I'm saying is if you're just looking at the d4x, this is just classical physics, but it is ignoring all the virtual fluctuations that could be happening in a theory which has a large number of e to the s of these kinds of virtual fluctuations. So that physics is not here when you write the classical d4x anyway. All that physics is actually hiding in the path integral measure dg. And you have to really do a path integral game, so once you start getting into a region where the dg, which is order e to the s Bekenstein, because that many states contribute, once this starts becoming important, you got to rethink everything, because it's not a classical problem anymore. As we had said before, the classical problem comes from taking e to the minus 1 over h bar classical action and only extremizing this and saying, I don't really care about dg, let's forget that. But the moment this starts becoming comparable to this, you got to start all over again. And the way I'm trying to now further draw a picture about, so the fact they are comparable, we've already seen. But how to now put the picture together of what it actually does when they become comparable in a way that respects causality, assuming that's the basic theory, basic property of the theory, that gives rise to this kind of a picture. So it's only a picture, but I'm trying to hold in the fact that when new physics comes from this source, it comes from virtual fluctuations, what are the fluctuations doing, the fact that you should make an effective C, and to respect causality. Now we're just trying to put a picture together. There are no calculations here, just trying to put a picture together. Yeah. Okay? Yes, please.
So I have a question about the structure of these macros. So are they called macros? Yes.
Yeah, that's what I'd call them. Yeah.
So you're suggesting an object which cannot be compressed in a certain radius. Okay?
Yes.
So it is either made out of only one thing, or it is made out of some particles that, not particles, but some parts that are connected to each other as you're showing.
No, it's made of things which are connected to each other. The simplest example of that, we had given this toy example, right? Like with the Euclidean short shell metric, right? I don't know where it's gone. So this is the example of the Euclidean short shell metric I had done. And people have now made cases where you can keep making these, so there's a little hole in the middle and then it's like a bubble. And then you can have made cases where these bubbles are joined together. So people have made cases with multiple bubbles.
So how
Okay.
do they join together?
Oh, so what happens is, so this thing doesn't want to compress because, okay, if you take just the Euclidean short shell geometry I showed you, there you can check. If you try to squeeze the size of the bubble, it wants to fight back. Okay? But now what happens is this thing expands here, and then like I've drawn in this picture, you can make another bubble and make it contract here. So you can join two bubbles to each other. Okay, there's a paper which we can take a look at the explicit metric. And so you can make more complicated objects which also don't compress.
But naturally, when we have an object that cannot be compressed in a certain radius, in other direction, if we pull it in two directions, it should be torn apart in a certain radius as well. But
That is true, absolutely. You could squeeze it this way and make it expand that way. But the point here is that if you try to make a closed-trap surface, you're trying to squeeze something from all directions. And just see how hard that is, because if the virtual fluctuations are e to the s in number, and you can't fit more than the Bekenstein number of amount of entropy in a given region, if all those virtual fluctuations could really be squeezed at no cost to half their volume, then it's really a little bit strange, because we don't expect to put more than Bekenstein entropy in less than area A. So I think any one guy, if you squeeze it this way, it can squeeze out that way, and that's why all these vectors are here in this room. But if I just have like something moving through it, nothing happens. They just move out of the way, they just distort. You squeeze them this way, they just spread out that way. Nothing much happens. It's only when you try to make a closed-trap surface, you're squeezing it from all sides. And now you're trying to squeeze e to the s guys in an area which is less than the allowed by the Bekenstein formula, and then you'll find the pressure. And then the pressure is the P equals rho, which you get out of doing just by putting in the fact that you can't put more than entropy given by the Bekenstein value, and that's where the stiffness is coming from. So as long as you don't try to squeeze it from all sides, you think of it like water. It's easy to press water like this way, it'll just expand this way, and you're right about that. But if you take a bunch of water and squeeze it from all sides, it'll fight back very hard because water is almost incompressible. And that's kind of picture is here. Yes.
I'm still trying to understand this. So, it matters, if you're talking about the time evolution
Yes.
of a situation, it matters whose time you're looking
Okay. Yes.
at and what frame you're looking at.
Could do that. Yeah.
So let's say that I were to, like, get on the other side and dive into a black hole. And I look at it from observer at infinity. The observer at infinity would say that the black hole reaches out to meet me
Yes.
and engulfs me.
Yes.
And then over an arbitrarily long period of time, that disturbance of the horizon settles down.
Yes.
And then you could think that that's a very long-term process
Yes.
in which I get converted into fuzzballs.
Yes. Yes. I understand.
But on the other hand, if I look at it from my own frame, do I feel myself getting converted to fuzzballs? Or do I actually go to the center of the black hole and get ripped apart by tidal forces?
Okay, so the two halves of that question, so let me separate the two parts of that question. Firstly, there's a simple time dilation which has nothing to do with fuzzballs or black holes or anything. Even if I come near a star, any process which happens by the time I move from one radius to the next radius, I might feel it's a short time, but because of the gravitational redshift, somebody at infinity will feel it's a long time. So that's just the normal redshift story. And so it's true that whatever fuzzball thing is happening, forget what the guy feels for the moment. If I actually look at the process by which, the shell, which is made of, let's say, gravitons, is turning into these bubbles, that's actually a process which in the local time frame is happening over the Planck scale. The same thing as seen from infinity is happening over a time of order Schwarzschild radius. Right? So that's just redshift, and that is true. Okay, that's just time slowdown. Now, if you ask what does the guy feel, now that's more like the question of complementarity that we were discussing just before the start of this lecture. And that's a whole more difficult question, because now we are asking if the whole dynamics of the guy who's falling in, as he becomes changed into all these bubbles and brains and so on, if that can be given an effective behavior where he feels he's continuing to fall in. And that's a more difficult question. You can make a model of the evolution where he does feel so, do a first approximation, but we don't know if that is true. So I'm just separating that part of the question out because that's a much more difficult question. But the fact that it's actually happening, if you ask me for the time scales, in the local frame, it looks like to be just, everything is Planck scale time. You could start at 10 Planck times and come down to 1 Planck time, everything will be done.
So you actually believe that I would feel that within a few Planck times, crossing the horizon,
Okay, so that's the feel question. So let me just go back to what I was answering about the feeling question there. And so let me do it here. And I'm glad you asked that because it's something I had mentioned briefly at the end of my public talk, but now let me try to say it a little bit more precisely especially for people who have seen ADS-CFT before. This is the analogy which is actually at first a little bit striking. The way we think of ADS-CFT today is not quite the way it initially came up in '97 and Maldacena proposed it. So let's look at that. What Maldacena said was, look, if here you have a bunch of D3 brains, and you take a closed string which falls on it, and the closed string loop can just be oscillating in some oscillation mode, so you could think of it like a clock, and it's coming closer and closer. And when it hits the D3 brains, these calculations had been done a few years before that when D brains were discovered. When a closed string hits a D brain, it just breaks into multiple open strings, and the open strings then spread out on the surface of the brain. These are what are called gluons. Okay, so it's a very computable process. And if you ask any reasonable person if the clock which was made by this closed string oscillating, has it broken into pieces, he's likely to say yes. Okay, if you think this was a person and this was his heart beating, you would say the person has definitely died. Okay, as it turns out, that's not true. And the reason it's not true is that this picture, as Maldacena showed, you can replace these brains and remove them completely. The flat space part is here. So the clock is coming in, but all the dynamics that happened here can be replaced by an antidistant space, and this spreading of the wave function on the surface of the brains can be mapped into the string, just going deeper and deeper into ADS space. And now the guy hasn't felt anything because he's keeping on pulsing exactly the same way as the clock did. And that looks very surprising. Look, didn't he break into lots of pieces? Well, he did break into lots of pieces, but the pieces were actually not random pieces that flew out like when you explode a bomb. They were actually a very particular coherent state of a strongly coupled theory like a liquid drop, and that particular state then just keeps spreading and spreading, maintaining only one particular profile. There's only one low energy state there corresponding to the string of this energy. Other states are gapped. It's a very big gap to anything else. It's a one particular state which just keeps spreading, and that state actually maintains the same dynamics and keeps containing the same frequencies. And so in fact, even though it looks like you broke it into something completely different, the effective dynamics can be mapped by a complicated map, a unitary map, let's call it U, into something which doesn't feel anything. And this is why the question of what you feel is very complicated, because even though when I fall onto a fuzzball, if I put the whole thing in a computer, it is definitely true that the falling string will get broken up and get converted into the little strings which were making the fuzzball and make it into a bigger fuzzball. That is true. You put the whole thing in a computer, you get that, which is the analog of getting this. The question now is whether this motion and the further evolution of this fuzzball can somehow be given an effective description that looks somewhat like you feel you didn't actually get hurt. Okay? Whether that is true now depends on the dynamics of the fuzzball, because here depend dynamics of D3 branes. If I replace these by a bunch of metal sheets and you jumped on them, you would get hurt. But if I gave you 1,000,000 D3 branes, if you trust Maldacena, jump on them, nothing will happen to you. Okay, because you will actually get broken to open strings, but you won't feel anything. So the question of feeling actually depends on what's the effective dynamics of the bunch of fuzzballs which you actually create. And the important thing, of course, is that this is, in ADS-CFT, this is an exact map. For the case of the fuzzball, the map can only be approximate. And that's because every fuzzball is a little bit different. That's why it can radiate different amounts of information, different information from each fuzzball surface. But if you actually fall in with an energy much bigger than the temperature, which is true for something like me falling in, the temperature for black hole is very low, then the conjecture of the complementarity would say that the dynamics of the fuzzball, even though the fuzzball you're breaking into strings, you're doing all these kinds of things, you can approximately map that into as if you were falling into the center of a black hole for a while. And the place where the approximation breaks down, you can say that's when I reach the center. So you can sort of play with it and show the scales are roughly right to make it work, and you can make a toy model. We wrote a paper about this, where the evolution is such that it can make this work. But just a toy model, I don't know if it is true. So asking what the guy feels is a very different question from first asking what actually happens. Because if you really have nothing there, it's actually the vacuum, you might say, okay, then I go in and I feel nothing. Here the guy feels nothing, so if you can approximate that, maybe there is nothing. That's not the case. The first question you should ask is, whatever I have here, if it is really the vacuum, does it or does it not create the pairs? If it is the vacuum, you can't stop it from creating the pairs. If you make a small correction to that, we've already learned from a small correction theorem, it doesn't solve the problem. So I have to change this thing completely, which is what we saw from the fuzzball. After I've changed it completely, you can now ask if something with E much bigger than T falls in, he will just become more strings. There's nothing like actually going in a computer when you do the whole thing, it'll actually become just strings. It'll become like this. But now you can ask, is there some approximate way where the collective modes of this fuzzball have the frequencies which can be mapped with some horrible unitary map to freely falling in, and that is possible. And then you won't feel it, or you approximately won't feel it. Okay? So it's a very interesting question whether you have this kind of fuzzball complementarity, and I think it's very hard to prove either way.
As a description of the same process in two different frames of reference, one being carried by me and one being carried by the black hole as a whole, or the surface of the black hole.
So I think that's a dangerous language to use for the following reason. Actually, this map doesn't have anything to do with coordinate transformations. Because for a while, people were thinking, look, short shell coordinates break down here, critical coordinates do this, there's one reality for short shell, there's nothing like that. Everything is covariant. If one set of coordinates breaks down, just like being near the North Pole of the Earth, just use other coordinates. The fact that you will actually, if you put the whole thing in a computer, actually break into the strings and become a fuzzball is a covariant statement in every frame. The only thing is whether the further collective oscillations of the fuzzball can by unitary map be mapped to the oscillations of an observer. It's a completely... But it's not the frame of the original metric. That's what I'm trying to say. Yeah, you've made some completely huge unitary as big as transformation as big as the one for ADS-CFT duality, that kind of unitary, and now indeed the oscillations of the string, you can call that your new frame. But the oscillations of string really, in terms of the actual exact picture, are actually the spreading of a large Yang-Mills bubble over here. So that's not a new frame. I mean, it's not like a new frame here. There's nothing like this here. It's just a big collective modes of a big Yang-Mills theory. So the reason I don't want to jump to calling it a new frame is that it's misleading to think that in the Schwarzschild coordinates, the black hole looks like this, and the Kruskal coordinates looks like that. That was some games that were initially being played about a decade ago or 2 decades ago. But that's not part of the truth. The actual metric of the interior has completely changed. Because if that wasn't the case, the whole problem with that frames game is, in some frame, if you have a Kruskal, a smooth horizon, any one frame, if it has that, in that frame you will get a pair produced. And then this guy will go out. I don't actually care whether I can follow the inside guy any further in this frame or not. If this guy goes out, it's already entangled with the guy going in. And then I don't care about this further. If two things have once gotten entangled, what happens to that guy, I don't even care. The entanglement of this guy with that system has grown by log 2. And that's the information puzzle, right?
But I'm still thinking that I can't feel that something has hit me when I go through the surface, when I go through the event horizon, that I conclude that the inside hasn't changed.
No, so it's not that simple. The problem is that these are two different sets of modes, because if you go back to the Penrose diagram for a black hole, a guy going in is this guy.
Yes.
And for him, suppose there's an effective description where he approximately looks like this. I'll draw the approximate with an arrow. Okay? The question of Hawking radiation is whether these outgoing modes still create pairs or not. So if you actually had, this is the mistake that a lot of people were making, if you ask whether space-time here is approximately normal, and that means both for guys going this way and this way, and suppose your answer is yes, you can't solve the Hawking puzzle. What you end up getting is, this guy is completely gone. There's nothing normal about that. You actually don't get those pairs at all, because you don't get the horizon. For these guys which are falling in, only for those guys an effective geometry can be created which sort of looks like infall. So I try to draw the Penrose diagram like this. This spacetime exists only for infalling guys as an effective measure. It doesn't exist for outgoing guys. And that's the way this actually differs from ADS-CFT. Because in ADS-CFT you would really get a space here where if you look at the right cone, you can both go out and you can go in. You can go in and out in the ADS geometry. It's a real piece of spacetime. But you're getting only one-sided spacetime, only the going in part. The outgoing modes just don't see a vacuum where they can be created by the normal way. So it's not an approximation to spacetime anymore. So Fuzzball complementarity doesn't say that you can get a patch of spacetime. If in any theory you got a patch of spacetime where the pairs could be created, you have no way out, because in that picture, this guy coming out has increased the entanglement here. Now you don't care what degrees of freedom you do. At a later time, you do some reshuffling of degrees of freedom and you again see a pair coming out. Whatever happens here doesn't matter. Entanglement now increased by a further log 2, and you keep going. So even for a short time of order m, around the horizon, there cannot exist a picture where the physics was normal for outgoing modes. Yes?
Actually, if you compress the vectors like this or like this, the compression rates are changing. What's the signification of compression rates?
You mean they want to compress one?
Changes when the compression changes.
So all you're doing is, suppose you compress it this way, the guy can just expand that way. So that's not a serious problem for it. That doesn't cost much energy because the total area remains the same. Right? The problem comes if you try to compress it in all directions, and that's what happens when a closed-up surface forms, because then it is forced to compress in all directions. And then the energy really goes up. It's easy to distort it like this. So as I said, the energy is like water. If you compress water this way, it can go out that way. But if you compress from all sides, it doesn't want to compress. Something else will happen. Okay. Anything else?
We have little time left.
Yes. Okay. Let me stop here then. Okay.